we are going to see something that is pretty useful when we optimize on top of doing decision making. Where one of the most common, let's say, combinations of linear programming and AHP, besides the one that you will be doing, is resource allocation, where you have a group of alternatives and an available amount of resources. Now, these resources could really be anything. It's not just humans, equipment. They might very well be amounts of money. So it could be a resource allocation with respect to budget. And what we try to do is use AHP to evaluate the added value of each of the possible solutions, and use optimization to do the resource allocation, trying to maximize the added value while keeping the resources under the given amount. So while being under budget, if we are going to use the budget. So first, you identify some possible solutions. You can brainstorm to get the possible solutions. You can solve mathematical models. You can simulate the situation that also would give you models, solutions. Second step, you will use AHP and ANP, AHP for you, to evaluate the alternative solutions. What brings value to your decision? Which align better with the strategic goals that you have? Which ones provide more chances for new collaborations or better use of the existing strengths of the company? Which will be easier to be accepted by the personnel? All these things are things that can add value to your decision. And at the third step, I use linear programming to allocate the resources to the alternatives. So to balance out between, for example, budget and added value. And let's see an example. We have a small manufacturing company that uses flexible manufacturing cells to produce 3 different products. It's a group of computer-controlled machines interconnected. Each product requires different steps, and that means that has also different timing system, different demand, different cost, all that. And you see a little bit on how the simulation of this model works. We simulated the process for incoming parts over 1 work month, okay? We have seen that the competition has started producing a new product, and the demand for this product is expected to be very high the next 3 years. Our production manager is concerned because products B demand has been unusually low the last quarter. We are already producing A, B, and C, and we are evaluating whether we should change the product mix and or add product D to the production mix. What do we know about these products? This is information that I received by running my optimization and simulation models. I know processing time for each of them. I know what's the per unit profit and what's the time in the system. How long does it take from the moment that the parts arrive until the product is ready to be shipped? For example, you see that I have a high timing system for product A, while for product C, I have a very low timing system. It's very easy and fast to produce. The first decision is, which 3 products should we produce? We don't want to have 4. We don't want that many. We had a meeting with all concerned parties, and we're trying to find what are the decision factors that we should consider for the decision. Our operations manager gave us the gray ones. Profitability, processing time, expected time in season. That's what they care about. On the other hand, other people in our group talked about the demand. They cared about the fit with the products. They want to have a set of SKUs that they can market that it will not hurt the branding of the company. And they want something that aligns to the company's goals. How are we going to combine the tangible and intangible factors to make hopefully a rational decision? First approach that you see is an AHP model that we were talking about. Then yes, I have all my criteria. See, I didn't even get into the process of breaking them down in clusters. I said I can handle 6 criteria at once. You already knew that I have numerical values for a few of them, so it won't be so hard to compare. And instead of alternatives, because these are my alternatives, I'm deciding which product mix to produce in order to optimize the process. Let's see. Pairwise comparisons, that's what you see. How did I get these numbers? I really put my stakeholders in a room and I all led through questions to get whether they prefer demand, they find more important the demand versus the profit. Obviously, they said the same. Demand versus sorry, demand is more important because it leads to profit and we like profit. And it goes on. After this discussion, we managed to have our priorities, which show that profit is the highest priority. So the most important criteria in our decision should be profit, followed by the demand, followed then from the 2 yellow ones that are pretty much the same, fit and alignment. So not harming the branding of the company is pretty important for them. And last, processing time in system. Now, not always the case that we put them that low. The fact is that in this specific company, the last few years, the demand is low. They have plenty of ability to handle production. And so they don't care that much whether it will be slow or not. They just care that they will be able to sell the products and that the products match their marketing setup and their branding. Some of the criteria, I told you, we got them from our simulation and optimization processes, and I put the values correctly. Timing system, I don't want in a factory to have my products for a long time in the system, so I inverted the timing system. The more they stay in the systems, the less good is the product. And from that, turns out that product C is the best product, is the one that has the lowest timing system, while products A and D are equally bad. Good thing that they said that they don't care that much about the timing system. For processing time, yeah, it was product C that was the best one because it had the lowest required amount of time. With respect to profit, let's go the other way around. Products A and D are more profitable than the rest, and you see, $20 and $22. No judgments here. These are all results of the simulations that I did and the data that I was able to collect, right? Now, these are the qualitative data that we have. Demand, fit, and alignment. You know, demand could be also quantitative, but we didn't have enough information about the new product that we want to add to be able to make fully quantitative. So products A, B, and C are already there. I know the demand. What we don't know is the demand that corresponds to product D, the new one. Based on the forecast, we were able to find out that what we know is true. Product D, that's why we suggested to add it, is the one that we expect that will be the higher, will have the highest demand, followed by products A and C. While product B, as our operations manager already told us, has been declining in demand, and it's ready probably to be removed from production. With respect to fit, product A is the first product that the company was set up around product A. That's why it has the best fit. The company is product A. Product B was added early on, and it's really in the same family of products, while C already, and even more, don't fit very well because they are the newest products. They hasn't been even added, and also at the same time, diversifies their production. So they will have to consider rebranding in order to be able to accommodate a new line of products that will look or be differentiations of product D. And alignment gives you a similar perspective. A is the heart of the company, so it's fully aligned to what they have. B and C exist long enough to have already created processes that handle them correctly. D is an unknown factor. They don't know what will happen with it. Same way that we did anything else, calculations say that we should go for A and B. That was the idea. That's why they were evaluating. Now, if they want to keep 3 products in the production, the choice should be B, C. That was the thing in the next slide. When they got into this game of trying to decide, they had a clear idea of what they wanted. They wanted to keep B for this product and replace C, D. What they found out is that probably that's not the best idea. And they were pretty skeptic because they didn't tell them to take out the production. We were just asking them to replace an old product, product B, that nobody wants anymore, with product C plus D. Now, this is how an AHP part would work. One more sensitivity analysis just to see how it looks. Finding out whether the solution is robust. Product A is the red one, B is the blue, C is the black, and D is the green. Well, first sensitivity analysis graph that tells us the obvious, that means that the model is working correct. With respect to demand, or as the priority of demand increases, product B becomes more and more valuable for my production. So this is the one that is led by, and as our priority to the demand increases, product A becomes more and more important in the solution. While B and C are pretty low, although C is obviously better than B, because C still has a demand. B is the one that has the decline. Is the solution robust? This vertical line shows the actual priority of demand. The actual priority of demand was at 0.3, 31. So quite close. I would almost be ready to say that the solution is not robust until the moment that I realized. What does it say? Right now, I have decided that I'm going to produce A, B, and C. The rank reversal never says that instead of 35, 32, I should do 32, 35% for A. Very small difference. So that would be evaluated. So yes, technically it's not robust. However, practically it is. What about I actually nothing changes no matter the priority of profit for the first two, because they have a very small but very clear difference of $2 per unit. While the more you care about profitability, the more B becomes a better solution than C, because C gives me 5, B gives me double that amount. So the more the profit becomes important, the better, the more appealing solution is product B versus C, which makes sense. Actual priority for B, 13%. Same situation with demand. We are sensitive changes to the priority of B. Okay? The change will stay just in the verb, the 32% to 35% and backwards. So it will not really affect the zero. Processing time. Processing time is down here. Run reversal at 40%. Okay. That's robust by itself. This makes sense. Yeah. The more you care about processing time, the less products A, D will be good that require a long processing time, and the more appealing products C that has the lowest processing time, and B will be. So it follows what it should be following. Alignment with a company. The more you care about the alignment, the more the old product will be a better choice than the new product. Robustness, let's see. Alignment is at 11%, at 50%. But we present the same situation as the priorities of these two increase. Product A becomes a better choice, or should be a bigger part of the product mix than product B, that is the new one. So if you care a lot about the branding, then introduce a small part of product B. If it is more important, then keep B as your priority. Timing system, process time. Robust, but refer and give priority to C that has the lowest processing time and timing system. But we haven't seen any linear programming yet. Here it is. We have one of the factories providing us with material X. We produce use all our products. It's one of our main common materials. Will be in shortage for the next 4 months. We have a quantity in stock that we will be using. However, we have to decide what mix are we going to produce and how are we going to work through this shortage of materials. What did I do? I have the units required per product, and where effectiveness, you read the priorities that are calculated from the AHP model. Then we have the actual use, that is units per product times the number of units that we are deciding to use. And we have the actual performance score, that is units produced times the value that they bring. And the total used needs to be less than or equal to the available. That's the budgeting part of it. On top of that, I have also some balancing constraints. B, C need to be produced at least at 5%. D needs to be and not be more than 40%. In other words, I'm making sure that I'm going to still produce some B's and some C's. We haven't decided yet to take out B. Okay? And over here is first the decision making and then the optimization. I use the decision making to do my evaluation of the value given from each of the options that I have for product. And I use the optimization to allocate my resource, the resource that wasn't in big quantities available. And this is kind of the way that we usually use the combination of the two.